Now we're going to be doing simplifying radicals, and essentially this is a really big test in whether or not you can see factors of numbers. So I'm going to write this down right here, really big. I want you to pull out of your brain from years ago factors, and I'm talking about numeric, meaning numbers, and algebraic, meaning x's and y's and z's and k's and n's and stuff, right? Variables. Okay? So for example, if I said what are the factors of 12, I want you to say 4 times 3 or 6 times 2, etc. If I said what are the factors of x squared y, I want you to think of xy, all that stuff that we used to do. Especially think back to GCF days. But I want you to think of special factors. In particular, I want you to think of looking for factors. This is our motto here. Look for factors that are perfect squares. And that goes for numbers and variables here. Okay? So let's start with one that is maybe a little bit easier to get our head around. Okay, let's start with one that has a little bit more easiness to it. So I'm going to look at this one, square root of 12. I'm going to look for factors in here, factors of 12 that are perfect squares in themselves. So I'd look for factors of 12. Well, I see 4 and 3, and 4 is a perfect square. So what I'm going to do is I'm going to write this up like this. Square root of 12 is the same as the square root of 4 times 3. But now the quotient rule, or excuse me, the product rule for square roots means that I can split those up into their own square roots. Well, the square root of 4 is 2. And I'm left with the square root of 3. So the square root of 12, this number is the same as this number, and this is simplified because there are no perfect squares left in the radicand, and that's what we're trying to really get at here, is the simplified radicand. We want to have as little under the radical as possible. And now we have that. 2 is square root of 3. 3 is prime, so I can't divide it up any farther. I can do the same thing here with the square root of 28. I recognize that it is 4 times 7, right, under that radical, which means it's square root of 4 times square root of 7. That is 2, and I'm left with the square root of 7. So when numbers get larger, they may be a little bit harder to see. But for example, you just want to look for some things in here. I see 245. You're looking for perfect squares, right? So what are you looking for? You're looking for 4. You're looking for a 9. You're looking for 16, 25, 36, 49. These are the only things you're looking for in these numbers. So you can, even if you're stuck, you can pull out your calculator and you can just start dividing some things. So let's look here. Pardon my old calculator here. It still works great. Texas Instruments. So let's just do 245 divided by 4. That one doesn't work because it leaves me with a decimal. 245 divided by 9. Also no. 245 divided by 16. 245 divided by 25, 245 divided by 36. All these are giving me decimals. Do you see this here? So they're not actual factors. 245 divided by 49. Ooh, 49 times 5. So 245 is 49 times 5, right? And so what that means is that I can then write this as the square root of, 245 is the square root of 49 times 5, which is the square root of 49 times the square root of 5. Well, that's 7 times the square root of 5, and I'm done. Same thing's going to go on for 147. We check everything out. We find out that 147 is 49 times 3. So this is the square root of 49 times 3, which is the root of 49 times the root of 3, which is 7 roots of 3. Okay. Now let's go into some that have variables. Okay. And I want you to be sure that you have pulled up the notes, the alexmath.org notes on radicals, just so that you can look at there's a little chart at the bottom of one of the pages for absolute values and taking roots of variables, and it's just the convention that we use. Okay, so looking at something like this, I can look in here and I can eventually figure out that 252 is 36 times 7. If you don't believe me, 36 times 7 is 252 right there. See, 36 times 7, 252. So this is the square root of 36 times 7 times a. Okay, and the 36 is going to come out. It will be 36 and square root of 7, square root of 8. You can split these up if you want. Obviously, the 7's not going to go any farther. The a is not going to go any farther. So I would even just argue to leave them under the same thing and just call this a square root of 7a. And so we have 6 square roots of 7a. Here, the square root of 4x to the 4th is going to be x squared, and notice that the 125 is going to be 25 times 5. So this is actually 25 times 5 times x squared times x squared. Or rather, I don't want to get ahead of myself, x to the 4th, which would be x squared times x squared. But anyway, the square root of 25, so this will come out as an x, right? So the square root of 25 is 5, the square root of x to the 4th is x squared. What do we have left under the radical? Just a 5. Okay. Now we're going to look at some that are even more complicated. So, and you just take these one step at a time. Okay, let's do number 16 right here. The 8 will give us 4 times 2. The 4 is good. The x cannot go anywhere, and the y squared will come out as a y. Okay, so we have 3. We have we have the 3 coming out. We have a 2 coming out from the square root of 4. We have a y coming out from the square root of y. What do we have left under here? Well, the 4 came out and the y came out. So then we just have 2x. So this is 6y times the square root of 2x. Okay. Looking over here, notice that we have that's a really large number, but what you can find out if you look closely enough is that 448 divided by 64 is 7. That means 448 is 64 times 7, and 64 is a perfect square. So we're going to have minus 3 square root of 64 times 7 times x cubed y cubed. When we take the square root of a cube, 2 of them will come out. Notice that 64 times 7 times x squared times x times y squared times y. So I'm sorry, that's sideways. So notice that this will come out, and this will come out, and this will come out. Okay, so when we bring out the 64, we get an 8. When we bring out this, we get an x. When we bring out that, we get a y. And what do we have left? We have the 7, we have an x, and we have a y. So now this x and this y, in order to ensure that our cubed gets back here, we have to make these absolute values of those. Okay, so we have negative 24 absolute value of x, absolute value of y, and xy, 7xy. Lastly, we're going to look at and I should clarify for squares, these are all, when you pull out a square, it's always going to be absolute value, because if you don't guarantee that, you're not sure that you're getting the right y, because y times y is y squared, but so is negative y times negative y. Right? So we're just going to make sure we get the positive absolute value of that. Things to the fourth doesn't matter. So here, if you look at this, this is actually going to be 64 times 5. 320 is 64 times 5. And so this is minus 8 square root of 64 times 5 times x, y, z to the fourth. So this is going to come out and this is going to come out. When that comes out, it's going to be just a z squared. When this comes out, it's going to be an 8. Here we have 5xy, and so let's just clean it up. Okay, and last one I want to do here, this illustrates my point earlier of the absolute value on squares but not on fourths. So when my voice is getting sore, I'm sorry, my voice is getting tired. So the 100 is going to come out as a 10, the x squared is going to come out as an absolute value of x, the y to the fourth is going to come out as a y squared, and the z is going to be left over. So let's pull that out. Let's pull out the 10, let's pull out the absolute value of x, let's pull out the y squared, and let's leave the z under here. So we've got negative 80 absolute value of x, y squared times the square root of z. And just for fun, make sure that you're going back to the notes on alexmath.org on radicals and reading through those, just so that you get all the stuff written out for absolute values and stuff when you're taking roots of variables to different powers. So, taking the square root of an x squared or an x cubed or x fourth, so on and so forth. Okay, that's it.